Hello, my name is់I work at Joyce and Safety Systems, and I would like to present you an HMI driving simulator study where we compared an unbalanced motor with mechanical vibration transducers for vibrotactile forward collision warnings in the steering wheel. This presentation contains motivation and aim of the study, the study setup, some results, and a summary and discussion. In this study, two vibration technologies are compared as an application for forward collision warnings, namely an unbalanced motor with two mechanical vibration transducers. An unbalanced motor is a motor with an eccentrically mounted mass at the shaft ends, which generates an unbalance and thus vibration. This is state of the art, for example, for lane departure warnings in the steering wheel, but it is also used as smartphone vibration motor. However, it has some disadvantages in terms of weight, space, and feedback configuration because the intensity is not adjustable. And therefore, the idea was to mount two vibration transducers on the 3 and 9 o'clock spokes and use them as vibration technology. Transducers, also named exciters, are loudspeakers in which the magnet vibrates, transmitting the vibration directly on the steering wheel. These bring a few benefits compared to the unbalanced motor. They are completely software programmable. There's not more space in the steering wheel. They are lighter, from customer side individually adjustable, and adaptive to human perception. And conceivable is also a direction-related warning on only one side of the steering wheel. So the goal of the study is to compare vibration warnings generated by either the exciters or the unbalanced motor in a driving simulator study regarding usability. So in the study, we used a within subjects design, so each participant tested both experiment conditions. On the left is the unbalanced motor, or short UAK, which is installed in the 6 o'clock spoke in the steering wheel with a frequency of 72 Hz and an amplitude of 9 meters per second squared. And shown on the right are the exciters, which are installed in the 3 and 9 o'clock spokes with a frequency of 140 Hz and an amplitude of 5 meters per second squared. The experiment condition order was balanced to overcome carryover effects, for example, by sequence, fatigue, or practice that could have an impact on the results. The study was conducted in October-November last year, 2020, in our driving simulator in Berlin with 32 participants, 23 male and 9 female. We aimed to balance gender and age after the NHTSA guidelines, but due to COVID situation, this was not completely possible. The participants were employees of the company Joyson, but they didn't know which of the two vibration technologies was the newly developed one. All participants had a driving license, and none of them had any impairments in auditory or tactile perception. The experiment was conducted in the fixed-base driving simulator, half of a mid-size vehicle with automatic transmission. The dashboard, 2 seats, and center stacks are built from an E90 BMW 3, and the test courses were programmed with Scilab, a simulation software from Würzburg Institute of Traffic Science, and the road environment was projected onto 3 screens around the car. So since we had 2 experiment conditions, we also had 2 different 10-minute test tracks on a rural road with 80 km/h speed limit. Each test course contained 2 forward collision scenarios, FCW1 and 2, with corresponding dummy scenarios. And the warning situations were on test course B, a car suddenly came from a gravel road after about 6 minutes, and a car coming from left taking the right-of-way when turning on the EGO lane after about 10 minutes. And on the other test course A, a car coming from left took the right-of-way when turning on the EGO lane after about 4 minutes, and a wild boar crossed the road after about 10 minutes. And 6 seconds before the collision, the driver was warned by vibration and a warning icon in the dashboard visible on the picture top right. Our measures, the aim of the study was to compare both vibration technologies regarding usability. which is defined as the degree to which a product can be used by specified consumers to achieve quantified objectives with effectiveness, efficiency, and satisfaction in a quantified context of use. And in our study, effectiveness was operationalized by driving data, efficiency by reaction time and mental workload, and satisfaction by subjective measurement of acceptance and haptic feel. So the procedure of the study: after the introduction, participants filled out a letter of agreement, demographic questionnaires, and practiced driving in the simulator. Then they drove both test tracks combined with the 2 vibration conditions, and after each test course, workload and acceptance scale was filled out. After driving, both vibration conditions were presented again, and the preferred one was chosen, and an haptic feel questionnaire was filled out. So the study took about 1 hour. So coming to the results, we analyzed mean differences in the measures between the 2 vibration conditions with t-tests, and the first 2 and the last 2 forward collision warnings were compared to each other. Okay, so first we look at the driving data. Shown here are bar plots with the condition means. On the y-axis is the measure, and on the x-axis are the experimental conditions, unbalanced motor, or short UAK, and the exciters. The orange line with the star shows that the difference was significant. So we found a significant effect on standard deviation of speed in the second warning situation. With the UAK, the standard deviation was about 6 km per hour higher compared to the exciters. We also found a significant effect on time to collision. With the UAK, there was about 1 second more time to collision, meaning that the distance to the obstacle was higher. And we found a significant effect on the mean steering wheel acceleration in both warning situations. So for example, for the second warning situation with the UAK, the steering wheel angle acceleration was about 65 degrees per second squared higher. We didn't find any effects on minimal acceleration, lane keeping quality measures, or other steering wheel data. Okay, so looking on the reaction data, on the right-hand side, the pie charts show for both warning situations how high the proportion of braking in blue and of steering in orange was as first reaction after the warning. Most participants braked first, and we found a significant effect on reaction time in the first forward collision warning. Reaction time here is defined as the time between the accelerator pedal release until the brake was pressed. And with the UAK, subjects reacted about 310 milliseconds faster compared to the exciters. And also important to mention is that 1 collision happened with the exciters. In the questionnaire data, we found a significant effect on haptic feel, measured with multimodal virtual switch scale for users' subjective preference of multimodal feedback by dB-check. Exciters gave more feedback and were more sluggish according to the rating. No effects on workload measured with Nasser-TLX scale or acceptance measured with the van der Laan scale were found, and 63% preferred the exciters. Okay, so summarizing all these results, advantages of the exciters compared to UAK were a lower steering wheel angle acceleration, meaning less risk of tearing the steering wheel while maneuvering around the obstacle, and exciters gave more feedback and were preferred by 63% of the participants. Disadvantages of the exciters were longer reaction times between accelerator release and braking, lower minimal time to collision, meaning a closer approach to the obstacle, and 1 collision happened. Also to mention, no effects were found on other reaction data, for example, the first reaction after the forward collision warning or the reaction type, and no effects on minimal acceleration or lane keeping quality measures were found, and also no effects on steering wheel data, on other steering wheel data, and acceptance or workload were found. So from these results, we conclude that the UAK warning is more suitable for acutely dangerous situations requiring quick reactions, for example, in emergency braking situations, and the exciter warning is more suitable for less hazardous, dangerous situations.